we're actually going to go and change directions for our final 3 days of class. And the last knowledge unit kind of core area that we have to talk about in this class is encrypting data and keeping it private and doing all that good stuff. So, to start the talk of crypto stuff, we have to talk about hashing. So, hashing, aptly being an ironic day to talk about it, but the idea being that we're taking a bunch of data and generating a signature based on it. So we're not encrypting it because you shouldn't anyway be able to take a hash and go back or reverse it. So we'll talk about, though, there are different, that depends, because there's some hashes that's not actually that difficult to do that with. So the idea is that if you change the original data that you send into the hash function, that it's going to come out differently. Same with your signature is going to look differently. So your bank should be checking signatures on all of the checks that I'm sure you write. And when the signature looks different, they should deny it. But we know that doesn't happen in any way, shape, or form. Similar to when you sign the credit card terminal at the grocery store, right? How many of you actually sign it? My signature move is a smiley face. But, so that system isn't so functional anymore. But either way, the idea with a hash is it's a one-way function to send data in. So this should be, if we have some sort of application, how we store keys like passwords. But we know there's a way, or we know that this isn't really the case. So if you're hosting an application or something like that, and you have users logging in, you need to store their passwords in some way, right? So we've been down this road of some places store everyone's password in plain text, like so, right? And why is that a disaster in the making? Yeah, it's just there. So what problems arise with someone being able to just see a password? So if I was running a system, I could grab all of your passwords and go use it. Is that likely to be the case of what's going to really be the problem, though? Are you going to say we have some awesome new app, because that's the cool new thing? Am me as a sysadmin going to take everyone's passwords and go and start playing with people's accounts? I mean, it's possible, right? But that's not likely where the issue is going to be. Where is our issue going to be?
Someone else getting hold of it?
Who would be the other person getting hold of it? There you go. So the problem isn't necessarily that a sysadmin can go read the database. The problem is that at some point the database is going to get dumped, because that's just what happens these days. And all the passwords get dumped. So we hope that they're hashed, but they're not likely to be hashed. What's a way to tell if website XYZ is actually hashing your passwords or not?
Ask who reset it, and whether they tell you here's a link to reset it or here's your password.
Yeah, if whatever website or provider you're going to has the ability to show you your password at any time, then you can have your license to fire them. Because if your bank can tell you your password, they're obviously not hashing it. So they can tell you your password. They're clearly storing it in clear text. The other fun one I have dealt with is, we encrypt the passwords. You obviously can decrypt them because you just emailed it to me. So, right, that's a bit of a problem as well. So that's
not hashing them illegal, but they had to meet certain regulations before they can, legally operate.
Well, depends on who's going to enforce it. If you're on Twitter, who's legally telling Twitter? Who has the authority to tell Twitter that they have to hash your password?
Illegality because they're a bank.
No. Oh, no.
Banks should.
No, I would actually say banks are probably the biggest violator of this, to where they will email you your password.
Well, Wells Fargo has a limitation to the length of your password.
Yeah.
I changed my password just for Wells Fargo.
Because it was too big.
Yeah.
So
I
that
kept
actually
too much.
brings
Those
up another.
are the ones that just like transparently drop off certain characters. Like we only accept 17, but we'll let you type more.
Oh yeah, you can type as many as you want, but we're cutting you off at 17. So that's another one. If like based on hashing mechanisms, your bank shouldn't even be able to know how big your password is. It shouldn't be possible for them to tell. Because we'll keep talking about this. Hashes are a set length. You take whatever input, and the hash, the signature that you kick out, is going to be the same length all the time. Whether you hashed an A, or if you hashed 5,000 A's, or if you hashed a 4 gigabyte file, when you do an MD5 hash, it's going to be this big, and never bigger or smaller. So, yeah, there's something else fishy going on as soon as you're not allowed to use certain characters. Why can we figure weird things out if you're not allowed to use certain characters?
Well, certain hash algorithms can't accept those.
No, I won't buy that. If you're doing it, like that is the case, but so certain hash algorithms can't accept certain characters. No. Maybe like weird obscure ones, but the standard hash algorithms that you should be using should be able to take it. Like if I can take a 7 gig ISO and feed it into a hash function, you can send a $sign into it. Right? The character set limitation comes up when we're using some obscure database and we're storing your password in plain text, and the obscure database we're using doesn't support certain character types. So if you've played around with SQL Server, because it's a good time, you will notice you can choose your character encoding that you use. So the default, like on SQL Server, is something Western, Unicode, whatever. What that literally is saying is, this is the list of shapes that this database understands as far as characters and ASCII and all that's concerned. So decent databases really don't care. If you get into certain like Japanese, Chinese, like those kind of languages, then sometimes you'll have problems with it. You'll know that your computer has problems with it when you go to display something and you get squares. And there's supposed to be like language of some form there, and you're just getting squares. Your computer doesn't have the shape, like it doesn't know what that shape is, or that text or font is. So if you're a bank, that's why banks get picked on a lot, because banks are using like AIX mainframes running DB2, which is weird, and they're old, oftentimes just being slowly updated. So one doesn't just take a database and just flip the character sets that it understands. That's a bit of a process to do that. So if you've been a bank that's been digital for years but hasn't like switched platforms to something new, you might not be able to store a good chunk of the symbols that we would now expect you to use in passwords. So that problem comes up when your bank is, again, not hashing the password and they're trying to store it and you use a weird shape. The database doesn't know how to store that. So, yeah. Actually, hashing would be a solution to the bank's problem of not being able to store weird characters, because hashing pretty much always kicks out, what would we describe this as down here as far as character set? Alphanumeric. That's our hashes should typically be alphanumeric, meaning alpha as in alphabet and numeric as in numbers. That's all the hashes we're going to really have in it. So that's what we would hope for. So hashing passwords, if you're a bank, would actually solve a ton of problems. But they don't, obviously. Some banks do, don't get me wrong. But yeah, if your bank can tell you your password, if your bank can say you can only use these characters, or if, not just banks, so anyone, or if you are restricted on the character sets that you're allowed to use, there's something fishy going on with how they do passwords. Not saying that's always the case. Like, they might just have some stupid rule on their web form that caps you at X character length or something like that. But chances are good there's some greater problem going on there. So the greater idea here is when you set your password, you should provide it, and then whoever you're providing it to, when you go to actually create your account or reset your password or something, should run your password through a hashing function. Sometimes they run it through many times in a hashing function. So if you hash a hash and hash it and hash it and hash it and hash it over and over and over again, that there's many iterations of the hash. So if your password is hello and we hash it 10 times, store that in our database, and away we go. So at this point, I no longer know what your password is, and for the most part, I don't have an ability to figure out what your password actually is. So then when you go to log in, you submit a password and we hash it again, and then we look up your password out of the database, but all we're looking up is the hashes. We just compare the two hashes to each other. So that's what we should do. But are there ways that this can get screwed up? Yeah, there's bad hashing algorithms out there. So that's one area. There's other, just like some hashing algorithms aren't meant for security, because there's lots of different goals that we have when we're hashing. So, and sometimes they're counterintuitive, and sometimes because math is really, really hard, they're like impossible to achieve. So the first goal is that it's easy to calculate. And that, we're not talking about like you get out a notebook, paper, and pencil and start calculating out a hash, although that is technically possible. You're probably not going to do that because hashing algorithms are vast in the actual math going on. When we talk about they're easy to calculate, what are we actually referring to?
Easy for the computer, it's efficient.
Yeah, we want something usually that's efficient, especially when we have Wii computers that we carry around in our pockets, like a phone. We don't want a hashing algorithm that's going to take, like, to max out the CPU of the device for like 30 seconds, because you don't want that wait time in there. I have tinkered with this, so how many of you use something like KeePass? Yeah, so what KeePass is like LastPass, only you deal with making sure it's on your devices. You don't have a service that stores it and synchronizes it for you. So I was being all elite when I set up my database long ago and set up just this obscene hashing structure, so that's like impossible to break. That was great on my computer because this is like whatever, 4 or 6 or 2 or many processor cores, right? It's fine. It doesn't notice. I don't notice. I transferred that database over to my phone and went to unlock it for the first time and had like oh, this app sucks. Went and bought a different KeePass app. Like, this one sucks. Because I just thought the apps were hanging, and it was like a 30-second deal. Because the hashing was so hard that the processor of my phone was just like, give me a minute. So being easy to calculate has its, its pros and cons. There's a con to being easy to calculate, though, and we'll come back to that. Or, well, what is the con for a hash being easy to calculate?
Easier to crack.
Yeah, so when we start talking about cracking stuff, the easier the hash is to calculate, the more problem we're going to have. So the other one is it's hard to reverse. So we should say that the hashes we use are impossible to go from the hash back to the original text that we feed into them. And that, for the most part, is, the word impossible is kind of tough to throw around. If we take 1,000 characters of data and hash it and get an output of 50 characters of data, it's going to be really hard to undo that hashing because you just don't have enough data to do it. But there are other ways of reversing them that we will talk about, that we don't attack it mathematically, we just brute force it. So we just start trying to guess every possible hash. Then the other one that Sid said is collisions. So if I hash two different pieces of text, the alphanumeric signature that comes out should always be different. Does anyone know of a hash that's really bad at this, that's still kind of in use? SHA is not actually that bad at it. There's one that's way worse that's still in use. MD5, yeah. Like MD5 shouldn't be in use, but it is. MD5 is bad enough now to where if the TLS signatures generated, like when you browse a website, are based on MD5 hashes, most browsers will flip and say the website's security is invalid and give you the like, don't go here, which you immediately just click ignore and go to the website anyway, right? So that's a thing, is that they should be really, really unique. SHA-1 has just, like in the past few months, I think, come up because there's been a couple like super crazy collisions detected. Now, the collisions that we found in SHA-1 aren't like if something is using SHA-1 right now, it shouldn't be using SHA-1. But if it was, it's like, well, we're going to break it tomorrow? No, but next week we could probably brute force it kind of deal. So we know it's possible, therefore we should move away from it right now. So, yeah, we take our input, we generate a signature from it. And then the other thing, yeah, I'm not going to worry about us going through and like doing all of the math behind all of this. But what we can do, oh, I don't want to select a file. Yeah, what the heck? Let's do it anyway. Let's grab this one and compare it to this one. Oh no, that's it. Oh, and then the web page died. Well, never mind. I'm not gonna do that. So yeah, whether it's a file or a, yeah, that really made it mad. Whether it's a file or passwords or text or even just raw data, we use hashing for it all around. So the trick with this, though, is the type of hash we use in these three situations, back when we had our three requirements for hashing, are all really, really, really different. So if we want to validate data is legit, do we honestly care if the hashing algorithm is like secure or reversible necessarily? No. We want it to be really fast, and we want it to kick out a signature that we can quickly compare. What we do care about in doing data validation are collisions. So how many of you, it's a fun exercise, if we go to download, let's try Ubuntu. We're going to go on an internet adventure. Ubuntu 17, let's do it. Let's try server just because. And, oh, it's not going to tell me. Maybe. No. I bet sent, since it's for nerds, will tell us. If we go to get it, we want the everything. Oh, this is just direct links out to the ISO. That's also not what I'm looking for. Oh, here we go. How to verify your ISO. So when you download a file from the internet, like an operating system, generally speaking, when you go to download it, whoever you download it from is going to tell you, oh, by the way, here's like the SHA-256 hash of the file. Or here's the SHA-1 or MD5 or whatever. Here's the hash of the file. How many of you do anything with that knowledge? I don't do anything with that knowledge. What are you supposed to do? Yeah. What you should do when, actually, let's try, if we go here and look for sent, And go to 7 and ISOs. In here. Does it have? Oh yeah, here we go. So here's a SHA-256 of all of the files that are hosted here. So once you have downloaded whatever, the CentOS Live KDE ISO, you should then hash the file. So the one way is it possible that there could be file corruption when you download something from the internet? Totally could be. What's the tinfoil hat reason for hashing everything you download?
NSA injected malware.
You went to like the official website of downloading this, and someone that's really crazy good at networking was able to inject data in there, yeah. So Big Brother injected malware into your operating system as you were downloading it. If you hash the file, then you should notice that the hashes don't match. And away you go. Then you're safe, right? So I do not hash files after I download them because I'm just not going to. It's just right. It's one of those things. If I need a CentOS ISO and I'm downloading it, I'm just going to download it and use it. I also have my personal little thing of if someone is good enough to inject malware into an operating system as I'm downloading it, they're also good enough to make sure the hash that I copy and pasted is going to be their hash, right? So there's that side of it. But that is your way of validating what you download is legit. The collision part of it with data validation is a big deal, though. Because if I can give you a regular file and I can give you a file that I have tampered with, and I can tamper with the file in such a way so that there's what we call a collision, as in when you hash it, the hash outputs are the same. That's great for me if I'm trying to tamper with you, but that's a failure of the hashing algorithm. So these are basically what we come up with, is that sometimes we absolutely do not care about security stuff. We just want it to be super, super fast. There's a certain type of hashing going on in your computer all the time that is totally, like, it's horrifically insecure. So we'll talk about that one first, I think. So this would be a cyclic redundancy check, a CRC check. Has anyone heard of this? The CRC errors were really popular back when flash drives started coming out. So if you, what was that? Was that how to remove? Oh, yes. Yes, please. The internet, you ask it and the internet will provide. So this was like, can't copy freedom. So the CRC error was like a really popular one to come up in Windows XP because around that time, flash drives started to really become the thing. And they were all terrible. Like slow and horrific and like just died all the time. So that's why I specifically searched for one. I'm sure I could search for like Windows 10 CRC error, and I'm sure they're there, but maybe not as prevalent. Oh, there's still how to fix this, please. Well, I suppose people still have their crappy flash drives, right? It's not like they went away. Yeah. So CRC checks are usually used when you're doing, it's just for quick and dirty data validation. So when your OS is interfacing to your hard drive, or you're interfacing to a flash drive or something like that, there's usually enough smarts going on to do a CRC check, which is just a really fast and easy way to check to see if the data was not broken effectively when you wrote it to the disk. So the CRC error, we actually, if we do like a CRC16, which is, your computer even does a more robust version of this now, but a CRC16, we basically take the data in some sort of numeric form, and if we have like multiple numbers or something like that, the last thing we do is we flatten all of it. So if we had like these numbers, say we encoded a file and end up with these numeric values, 1, 58, 54, 12, 54, 12, and smushed them all together. So we had, how many integers are there here? 1, 2, 3, 4, 5, 6 integers. So if we took these 6 integers, don't mind the 4 just yet. So we took these 6 and created a 7th integer out of it that's just all of the numbers squished together, and then do mod 16. What's mod 16 do?
It's the remainder after it's divided by 16.
Yeah, so if we divide this big number by 16, we got a 4 as the remainder. So when we go to actually transmit our data to your hard drive or to your flash drive, we transmit these 7 integers. And then to verify it, we check that when we mod 16 the written data, that we got a 4 back. If we didn't get a 4, we have a CRC error. Would you use this to protect a password? No, because you're going to have a collision effectively every 16 values, right? For writing data to a hard drive, that's fine. Well, then your computer now does things in a more complicated way, but still. This is also used a lot in wireless stuff. We do CRC errors or CRC checks when you receive a wireless frame to make sure, like, does the data seem to be somewhat intact? And if it passes this, we're like, well, it's close anyway. Because generally speaking, in the wireless world, or even when you're writing data to a hard drive, if there is a problem, the problem is going to impact like a vast amount of data, right? If you've like lost a hunk of data along the way. So mod 16 or mod 64 or something like that is going to more than likely pick it up without a problem. So that's our wanting super speed but not security. Then there's other times where we want to make sure that there are 0 collisions. There's other times where we want it to be really fast. And there's actually times where we want it to be really slow too. Why would we want it to be slow sometimes? It's the slow. There are deliberately slow hash algorithms out there, used for one specific purpose.
Inefficient.
Slowing the attacker down.
Yeah, they're like the pure. It's not even a compute. Yeah, I guess it is to an extent a computing power problem. It's aimed at if I'm trying to brute force a hash, it just is going to take me forever to do it. So one of the areas where the slowness kind of thing comes up, or that they're like talking about it, is doing passwords. So that if the hashing algorithm I use when you log into Facebook takes me, 3/4 of a second, right, to hash, is that a big deal for you logging in? No. But if the hashing algorithm takes 3/4 of a second and I'm trying to guess every possible password combination to break your hash, does that now have an implication to me? Yes, especially if we use a really fast and efficient one, if I can guess like 10,000 hashes a second, if I'm now down to like a hash and a half a second, that's like crazy what we do. So for passwords, we don't care about length, really, of the hash. We just want the hash to, more or less always be the same size, but we want it to be as unique as possible. So this is where the smaller and smaller the hashes are, you eventually run into collisions because there's just eventually so few possibilities going on. Kind of like with a bike lock. If your bike lock only has 2 digits and it's like the twisty number kind of lock, 2 digits, can someone brute force that pretty easy? Yeah, but then for every additional number you add, makes it exponentially harder to break. So the bigger the hash size is, the harder and harder it's generally going to be to break. So the other one is encryption. So when we look at, like, when you go to encrypt some data, is your password is that what's used as the key to encrypt the data? No. Why not? Yeah, we generate something based on your password. Because if we look at, and we're going to talk about actual encryption stuff next time, or maybe if this goes quick enough, we'll talk about it today. So if we go to encrypt something with like modern, really good encryption algorithms like AES, AES is pretty good and really hard to break. Really the only way is to brute force it. So if the key we use to actually encrypt your data is your password, is that going to be easy to break versus if the key we use is a hash of your password?
Is this a trick question?
No, I mean, like, think of it like that. Let's do actually, is there a command line?
It's just gonna help me determine my answer.
Nah, there's no. Okay, I thought I had a Shaw utility on here. So let's go look for what do we have here? All right, here we go. So if I want to encrypt data, the key, do I want it to be goats? Or would I rather it be this? That's what I was going for. I want to type goats into the computer. I don't want to type that monstrosity in there. But the actual key used to do the encryption of the data, I want to be this, because that's a far better key than goats. Can someone still try to brute force it? Totally. So if you want to try to brute force it, you now have a couple options. You can try to just start raw guessing hashes, which effectively means you have to try to guess this password here. Which,
Is that essentially a rainbow tables method?
if you try to pre-compute.
Yeah.
Yeah, it works to an extent. Okay, I'll talk about the rainbow table thing. Don't let me forget about rainbow tables. Or, well, no, I'm not going to forget about rainbow tables, because I was going to show something with rainbow table when we're done. So, yeah, I could try to guess and actually brute force. Well, actually, no, a rainbow table won't work for this. A rainbow table would work for saying this hash is goats. Rainbow tables can unhash something. But if I'm trying to decrypt something, then I need to know the actual hash value itself. So a rainbow table won't help me come up with this, because if I'm just trying to decrypt data, I have to come up with the actual key to do it. So then I would have to guess this whole password, and then try to decrypt it with that key, and then it's going to fail. The other way is I could try hashing, like try doing this, calculate, does that hash work? No. Try this, calculate the hash, does that hash work? No. And then I'm going to end up at like AA, does that hash work? No. So they're not good ways to try to figure those sort of things out. So that's why, there we go. We don't normally use these specifically to figure out encryption keys. What we would use is a stretching algorithm. So stretching algorithms are meant to take a key of some sort and then generate another cryptographic cycle on it to just make more data out of nothing. So what we would actually do technically in the case of like doing a database or encrypting stuff is we might take a SHA-256 hash of your password. We would then take that hash and feed it into a stretching algorithm that takes that, however big a SHA-256 is, it's 64 bytes long, which would take that 64 bytes and turn it into like, I don't know, 10,000 bytes or something like that, and then that would be the actual key used to encrypt stuff. The other fun thing about stretching algorithms is that they are super slow, because you're taking a little amount of data and just turning it into this huge monstrosity of data. So depending on how you set it up. So because of that, they're really, really hard to brute force. But if we know it's a person making a password, we're still better off trying to guess their original password and jumping through the hoops than we are trying to guess like a 5 megabyte key file, because that's just not, like, it's not possible to do that. I mean, I'm sure maybe it is hash or possible somewhere. A cool password testing thing for stuff like that. Do you ever listen to Security Now podcast? So Steve Gibson is the guy. I don't listen to it anymore. It kind of drives me crazy personally. But all of the things with Leo Laporte, the guy kind of drives me bonkers. So what am I looking for? Services, password. Oh, there we go. So his big thing, he's one of those like crazy weird security people, to the point that he's like, menus like this in the rest of the world would use JavaScript, and he somehow found a way to get CSS to do it and stuff like that. Because JavaScript is evil and shouldn't be used anywhere, and not that I disagree, but eventually you just have to conform. So he has a cool utility that kind of gives us a rough like guesstimation of how long it's going to take to brute force stuff. And they've got his like...
No, if you did this with CSS, I would be impressed.
This part. I can't imagine... Yeah, I bet this is not with CSS. I bet this is a lot of JavaScript. Oh, look at him. He's like, test your real password. Nothing will ever leave your browser. Because people, like, his followers were like, you're stealing our passwords.
What is it? You use a text disclaimer there?
Yeah, there's totally a disclaimer right here.
So,
yeah.
Is everybody in our field tinfoil hat wearers?
Not everybody.
Or just a lot of them?
Who's the ultimate one? It's not really a tinfoil hat wearer, just an interesting fellow. Look up Stallman someday. Sid got to interact with Stallman.
Many times.
Yeah. Stallman's the founder of like the GNU free software movement kind of thing. So JavaScript isn't technically like free and open and GNU licensed, so he won't have it. That was my favorite thing of all of Stallman's stuff. So if like the website of the event you're asking him to go to has JavaScript on it, he's like, I don't know if I want to go to your event.
It looks like an Indian name.
Stallman, yeah. I mean, he's a smart, cool guy, but he's a different fellow.
You know, this idea we have a long list of all these popular things he doesn't use and watch.
Yeah. It's, if you're up for some like digital people watching, look up Stallman and go to his website, and you'll learn a lot. And the guy, like, technically, like, he's not wrong on stuff. It's just he goes about it a little differently than most of us. So, anywho, what this does is gives us a rough guesstimate of, like, what the realistic, like, as a password starts getting bigger and bigger and bigger, even eventually once we get an exponential amount of A's in here, it's just not, like, we just don't have the computing power to actually calculate this password. I mean, we have the computing power to hash it and store it as your password, but we don't have the computing power to brute force it, because in order to brute force all of these A's, we have to brute force all of these and all of these and all of these, because it's an exponential curve of how hard it is to actually brute force passwords. So in the grand scheme of things, there are some hashes that are better, some hashes are worse. There's even instances where I'm like, yeah, I don't care that that's MD5 because it's fine. But then there are some hashes that are just wrong and should have never been a thing, but Microsoft managed to pull it off. So rather than using any of the standard hashing algorithms that are in existence, Microsoft decided to make their own. So this is where we have the LAN manager hash, or LM hashing. This is something that when you go to work someday is a good thing to check for inside of group policy to make sure it is disabled for your entire network. The problem is disabling it doesn't do you any good until everyone changes their password. Because even when you disable this hashing algorithm on Windows, everyone's hashes are still stored using it until they change their password, because it's a hashing algorithm. You can't undo it. That being said, the policy, like in Active Directory, to fix this is store passwords using reversible encryption, I'm pretty sure. Yeah, here we go. So the hashing algorithm nowadays we know is so awful that Microsoft, the checkbox to disable it is literally store passwords using reversible encryption. That's like what Microsoft calls it now. That's their way of being like, hey, probably shouldn't do that, right? So what LM hashing does is it caps your passwords at 14 characters. That's the first fun thing that it does. It'll let you make a password that's 5 bajillion characters long, but like we were talking about before, it just cuts off the first 14. And that's all it uses. So you could have, like, assuming there's, like, this happens of people that somehow magically happen to have the first 14 characters in their password. If DSU's Active Directory network was using LM hashes, and you and I had a 28 character password and the first 14 were the same, we could log into each other's accounts. No big deal. Because Windows was just blissfully unaware of anything beyond the 14th character. So that's one. But it's one of those things that it just gets exponentially worse. Because even if our first 14 characters, let's say we mixed upper and lowercase, no, we uppercase everything in LM hashing. There are no lowercase characters. So if you enter your uppercase, lowercase, all that good stuff kind of password, that's fine, but when Windows takes it, it uppercases everything. So if you go to old Windows computers and set a password of, like, that's case sensitive, and then turn on caps lock and enter the same password, it'll work. Because when it would hash the password, it would uppercase everything. So that's fun. The other one that we now do, we start to get into some math love. So if your password wasn't 14 characters or 14 bytes, the algorithm only could work with 14 bytes of data. So if your password was 5 characters or some random number of characters long, it would pad with null bytes, up to 14. So up to now, what we have done, like if we come back over to this world, oh no, I wanted back on that other website. Here we go. All right, so there we go. So rather we had uppercase, because look what happens when you actually do an uppercase. On his little magic math, we take 3.43 centuries and then make it all lowercase to a little over a week down here by having all lowercase letters. Well, actually, in the case of Windows, it would be all uppercase. So, and well, no, let's give them the benefit of the doubt. Throw a number in there. So this is hard to crack, right? If it's lower than that, we know it's always still going to be 14 characters. So when we go to try to brute force something, we know 14 characters is the mark to always go for. However, Microsoft decided, after we've capped it at 14, we've uppercased everything, and we made sure it's always 14 characters, the next thing we did is we said, well, we're going to hash it actually using DES, which DES is not necessarily an algorithm you'd want to use. But the worst part is, rather than just using it on a 14-character password, it cuts your password in half. So rather than having a 14-character password, you really have two 7-character passwords. So when we talk about exponential math, the more characters you have, the complexity goes like way, way up, right? It starts to get way, way harder. So if we cut your password complexity or your password length in half, we don't cut the complexity to brute force it in half. We cut it by like many, many powers down. So that case would be when we come over here. So this currently takes, in their ideal situation, 2 years to crack. If we cut off 7 characters, now it's just like, it's not even something to be cracked. So I'll give it the benefit of the doubt and put a number in there. So that's a problem, because what we do when we start to measure key space is we do everything by powers. So when we have your keys being at 2 to the 92nd power, that's how you get 14 characters out of it. That's a big number. But since you have only 7 characters, it's 2 to the 46th power. And then since we know that there will never be lowercase letters, we just eliminated 26 characters from our search space to actually try to brute force. So what we can actually do, the entire key space of LM hashes can be, well, so that's where we get into rainbow tables. So the concept of a rainbow table, I don't think I talked about rainbow tables. No. Okay, cool. So the concept of a rainbow table is, why brute force them every single time? Let's compute them ahead of time. So if we go and run all the hashes ahead of time, we're good to go. However, with rainbow tables can be easily defeated by you trying to secure your stuff by just making a foolishly long password. Because the longer your password gets, the more it's going to take to compute the rainbow table to figure out the password. And eventually you're going to hit the spot of like, no one just has the storage capacity to actually store the rainbow tables for this. LM hashes, being what they are, whoops, I don't want a new thing. Since they're really, the longest password is only going to be 7 characters, and there's no lowercase letters, the hash of every possible LM password takes a little over 30 gigs of space, which is admittedly a hearty amount of space. But to consider, if we want to brute force a LM hash password, we don't have to brute force it. We can effectively just look it up and find out what the original password is. So if we come in, the idea being here, I'm going to make a password, and let's do how many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Put the symbol in there for some extra hard. So this machine is running Windows 7. The key thing about Windows 7 is that, or well, newer versions of Windows, is if the password was more than 14 characters, in these versions of Windows, it will disable LM hashing for the password. So that's why I'm specific to make sure my password is right at the 14 mark. And then we take our nifty little utility that we put together and start running it. So what we do is start running, potentially harmful software has been detected. So what we're using is our Cracky, which is just a rainbow table tool going through all the hashes. So I guess the first thing we do is use pwdump. So we actually dump the Windows SAM file, which is, the Windows SAM file is equivalent to like etc passwd inside of Linux. That's where all the hashes are stored. And then our Cracky goes through and starts reading all these. The fun thing that we do here, though, to make this a little more exciting, is we see this is a basically a 32 gig hard drive, and this is a virtual machine. Fast computer or not fast computer, it takes a while to read through 32 gigs of data off a hard drive, right? So the idea of just making the demo cool is that this computer has 45 gigs of RAM, and the rainbow tables are stored on not a hard drive, but a RAM disk. So that walking through 32 gigs of disk should be a relatively fast thing. So let's see how we're doing anyway. This is the fun thing. So if you run this, and you can go download like, whoops. There are many torrents out there. There we go. Project Rainbow Crack. That have many rainbow tables out there. You can download all of these if you would like. Eventually you get to the point where they will, like, you eventually start getting, like, it's going to be a rough go to start downloading some of these big files because you're talking about terabyte downloads. So they're also happy to just mail you a hard drive. So that is where we end up with never ever underestimate the bandwidth of FedEx. Because FedEx and a big hard drive with overnight shipping is probably going to beat a good chunk of internet connections in the world. Because if you put a box full of terabyte hard drives, that's tough to beat. We're still searching along here. So the fun thing is, as it's crawling through each one of these files searching for the password, you can actually see it's taking like 7 seconds per file, or give or take. So that's because it's on a RAM disk. If you do this on your computer, that's cool, because you can download and run rcracky on your own machine or wherever. This will take a little bit longer for the seek time through your disk, especially if you have a spinny hard drive, because your disk heads are going to be just freaking out trying to...
How long does it take to load that into the RAM disk?
About a minute or two. So that's the actual the bias of this particular little demo. Is this actual virtual machine hard drive is sitting on a 3-par SAN with like 180 disks in RAID 50. So it's not like it's slow anyway, but the RAM disk is just so much less slow. So still thinking along here. And that's actually the ironic thing is, I don't know why, but I gave this box a bunch of processors, and it's not like doing it. I mean, it uses 1 core because it does have to go through there. Oh, there we go. Bloop. So what it doesn't give us our total time, but 195 seconds of crawling through the RAM disk. So that's 195 seconds of data seeking. The actual, when we talk about cryptanalysis time, is it would load a hash that it's like, hey, maybe this is the one, or maybe this is the original text. I'm going to quick test to see. So between the cryptanalysis time, and then there should be false alarms, total chain walk step due to false alarm. So when it's going through here and stepping this down, it has a somewhat intelligent rainbow table data structure in that you can start to, like, you know that these passwords over here are not your hash at all. So you can avoid them. And it's kind of like going down a tree. So if you start walking down the tree and get out to like a leaf of the tree, and then you're like, was this it? Nope, I have to step all the way back now. So that's the number of times that it was walking down a branch trying to find our actual hash. So, yeah. And then it had 10,000 times that it thought it had the password, but it was wrong. The next interesting thing that our crack anyway does is the actual password is, this is the fun, newer versions of Windows store LM hashes and NTLM hashes, which are actually okay hashes. They're a SHA derivative, I think. So since they're stored side by side, you can't figure out the case sensitivity of an LM hash password because they're just uppercase. So after it's figured it out, it then knows the plain text of the password. Then it just does a brief brute force to figure out the case sensitivity on the original NTLM hash as well. So LM hashes are terrible is the lesson of the day. But the magic of it is they're still in use in many places. Not that people are deliberately using them, but it's usually a group policy thing that people just forget about being turned on. So when they start to go through group policy, see that that's turned on still, because it didn't used to be called store passwords using reversible encryption. It used to be called something else. So people go through and see that's still enabled, and they're like, oh no, that's no good. So, yeah. Anywho, that's Windows. Windows, you use whatever hashing algorithm Microsoft dreams up for you. And you'll like it, whether it sucks or not. Linux is modular. So if you actually cat your etc shadow file on a Linux machine, you will get something that looks like this. So the first little doodle in there is actually telling you what the hashing algorithm is inside of Linux. So ideally you won't see a lot of ones anymore. You should see newer things inside of there. So Linux can basically do, whatever, because it's Linux and flexible, and it's cool. So the final moral of the story, because this also happens a lot, where places will make their own. And is that ever a good idea? No. But some people sit around a table and are pretty good at math, and they decide, meh, can't be that hard. We're math people with a dose of developer inside. Let's make our own hash. It'll be better than using one of these off-the-shelf ones. And then there is a false sense of security in that, because if you make there's an initial masquerade of it being really secure. Because if you dream up your own hashing algorithm and you don't release it or tell anyone and you just use it internally and someone steals all of your hashes, can they undo it? They don't know how you made the hash, right? So that's the theory. In actuality, what happens is if you are compromised to the point that your database is being stolen of all of your password hashes, your hashing algorithm's also getting stolen as well. And then it's just all over with, because then it's really easy to walk through and find bad hashes with stuff like that. So, yeah. The last little doodles. So tomorrow or Tuesday we'll talk about encryption and start doing some VPN-y stuff. And I'm pretty sure this is how this is going to go down, is on Thursday or Tuesday or something like that. I think I'm just going to release a hands-on final of doing OpenVPN. So there's a caveat. So there's a perk to you get the final early. I am going to be gone the week of finals week. I will be in South Dakota for about 10 hours because I have a trip for one grant from NSA that I have to go on, and then I get back at 10 o'clock at night, and then I fly out again at 8 o'clock the next morning. So that's my finals week. So I won't be around to help if you wait until the final due date of closing of finals. FYI about that. So that's why we're being flexible, but pretty please don't wait until the night it's due, because I'll probably actually be on a plane when you're emailing me, and I'm not going to pay for the plane's crappy Wi-Fi. So.
Do you have any idea exactly what you think we're going to be doing with OpenVPN? Because I was planning on making my own OpenVPN server anyways.
Oh.
So, it'd be kind of cool if my personal project could be the final.
Oh no.
It'd make it easy.
Oh no.
Oh, you should make
No.
it twice.
Just because you do it, no, there will be there'll be specific requirements to this one.
Rip the dream.
Yep, crush that dream. But
I'm sufficiently crushed.
yeah, Good. I like to make sure that all of my students have a sufficient amount of squishing under the thumb. Crush all the hopes and dreams. That's how I roll.
Don't get too far.
Does anybody have any other questions on stuff? Parker?
So you said don't make your own hashing algorithm. Is there a specific group or organization that makes the new ones or makes updates to them or whatever?
So basically our question is, where do hashing algorithms come from, right? So typically what happens is some large body like NIST, the National Institute of Standards and Technology, there we go. What they will do is get a boatload of money put together and say, we're doing a crypto challenge or a hashing challenge. And if you win the challenge, you get the boatload of money. So that's one way. That's how like AES came about, is through one of NIST's challenges. And that's a cryptographic thing, not a hashing algorithm. But that's usually how it comes about, is someone puts up a bunch of money, a bunch of people work on a bunch of examples and submit them openly into the community to be judged. And someone picks like the reigning champion. The other ones are all still there. So we'll talk about that actually tomorrow or Tuesday with encryption, because there's a specific how we use AES or why we use it is because of one of NIST's things. There are, of course, people that don't like that because that's a government agency and Big Brother and all of that, but that's kind of when you get a bunch of mathematicians openly submitting and like open source kind of algorithms, I'm like, well, I'm not that worried about it. As opposed to Big Brother saying, here's a chip that you're going to put in all of your devices. No, I don't want Clip's chip. Maybe I'm spelling it wrong. Is it Clipper? Oh, there we go. So this was a closed cryptographic challenge put out by the government that was a key escrow that said, all of your data will be encrypted and protected. We also have a key to unencrypt it, because this chip would do a key escrow with government agencies. Guess how well that caught on? Yeah.
But they do use that still. Kind of,
The Clipper chip? Well, this is like back in the 90s they tried this.
because I know, like, you know, if a nuclear sub goes down, they blow up the front of the ship.
Not sure. This is a cryptographic thing.
Well, yeah, that's why they do it. They
Um,
focus on it.
But I would say, well, that would be actually very similar to how Apple has their secure enclave in devices. So there is actually a mini computer inside of iPhones that stores all of the data needed to decrypt the actual memory of the phone. And in the event that you piss off iOS to the point that it's like, no, it's over with, it doesn't format the storage. It destroys the data in secure enclave. So what it does is destroys the encryption keys. So the data is still there. You're just never going to get it back because it's gone. That's not a key escrow though. The key escrow would be like, you can encrypt your data and decrypt it, but so can I, because I have the ability to unlock the door as well.
Okay.
It's kind of like a multi-mastered system for doors.
Okay.
Like, you can get into this door, but I can get into all of the doors, is how that works. So, anyway, we'll see you all on Tuesday.